unless there's some specific reason we need to. Um, does anyone have any questions? You can post them in chat too.
I don't think it's me. That's this. I don't smell. It's this. I smell the same.
All right, so we're talking about. Oh, and there's another quiz. So I think most of you did the quiz, so that's good. So you're checking Canvas, so that's good. So there's another quiz today. There'll be a lot of them. They're just there to make sure you're.
So I missed the first quiz accidentally because I forgot until I saw your post today. Did I already just do that quiz?
What post? I didn't post anything.
Oh no, I saw a message saying, about we're gonna have class, and I was like, oh man, that's right. I had to do that quiz.
Okay.
Yeah. So I took a quiz, just really quick on my phone, just to see if I don't think that was the quiz because that one was about like it was just taking the determinant of a 2x2 matrix, the 0, 1, 1, 0.
That's the first quiz, yeah.
Okay. It let me take it, still.
Yeah, you can take it and they're available. It's just I'll know if you submitted it after the 24-hour deadline.
I sent you an email. Apologize. I'm sorry. I completely
all right.
forgot
No,
about
it's
it.
all right. And there'll be a lot of them. It really won't affect anything. They'll just be able. Just be sure that when I say it during class, just fill it out real quick. Either during class or after class. You get 24 hours to do it, but there'll be a lot of them.
Okay.
So it really won't matter. And again, they're not. I'm just checking for completion. So
yeah,
like. Well, most people did well on this first one. Actually, everyone basically did well. They got like anywhere between 3 and 5 points. But
yeah,
again,
I did it in my head, the 2x2 matrix, and like a dope, I realized that it should have been a -1, not a 1, but I just was like, oh, 1.
yeah. Well,
Yeah, I
a
know.
little bit of a tricky one because
that was easy. That actually, if you put that on the test, that'd be great. I was able to do that in my head.
Test is harder than the quizzes. Quizzes, yeah, it's supposed to be pretty easy.
Nice. All right.
All right, so we're doing spectral decomposition, and we have this theorem about Hermitian matrices, that a Hermitian matrix gives you a basis for your Hilbert space. And it's got a lot of nice features. It's got real eigenvalues. And it provides you, the eigenvectors provide you with the basis for your space. And that's very important when we actually connect this to physics, which we'll do today. Today is kind of an important class, sort of unfortunate we have to do it online, but well, maybe I'll go really slowly and then I'll never get to the important part and we can save it for next week, but
yeah, do that.
Yeah, but okay, so I wanted to, so that's for Hermitian, and we showed that last time, that we have real eigenvalues. And the basic idea is, I don't know if you remember from linear algebra, once you find the eigenvectors, you can construct a matrix that's like, has the eigenvectors as the columns of the matrix. And then you can use this matrix to transform your original matrix to a diagonal matrix, which just has the eigenvalues. And that's that unitary that I was talking about last time. There's a unitary U. So the three things is there is a unitary operator U such that what? Such that you can make a diagonal matrix out of your original matrix. So you multiply it like this, and you can check it out. You should play around with Mathematica or something and see how it works. Maybe we can do that since it's online, so we're gonna sort of take it easy. Maybe we can try doing it here in Mathematica and see what goes on here. So
Do all the eigenvectors have to be normalized before you do this? Is this unitary?
That's a good question. Yeah, I think so. Yeah.
Okay.
But let's try it. We're just gonna play around. I haven't really. So let's make a Hermitian matrix. Okay. So let's put some entries in here. We'll put some complex ones in there just to make things a little less obvious. So let's just try stuff. So remember, Hermitian in finite dimension land is just the transpose has to be equal to the transpose plus the transpose and the complex conjugate. And that has to be, if you do both of those things, that has to be equal to the matrix itself. So if you have any imaginary pieces, then they can't be on the diagonal. And if they're on the off diagonal, then the transposed element has to be the complex conjugate of that. So if I wanted to construct, so I'll show you what this looks like in a moment. But okay, so hopefully, let's see, 2, and this one has to be 1. Okay. So all right, so it looks like I did it right. So what did I do here? I made, if I have an I here, then a Hermitian guy must have minus I in the opposing corner. If you have a real value here, then it has to be the same as the opposing, the transposed element. And then same thing here, and then diagonals have to be real. So what do we know? We know that the eigenvalues of this, right, should be real. And they are. There's some numbers. There you go. Some complicated numbers. All right. And so what do we want to do here? We want to find the eigenvectors. And I showed you how to do that earlier. But okay, let's look at this. So let's try to construct this unitary. Maybe we'll try to do it sort of numerically. So, all right, these are the eigenvalues, and this is the corresponding eigenvector. So I haven't practiced this, so it'll be an exploration. We'll see if it works. So what we're gonna do is take these eigenvectors, right, and try to construct that unitary that transforms our matrix, our original matrix AA, into a diagonal one, which just has this on the diagonal entries. So I'm going to try to do it. It might fail, but we'll see. So I'm going to copy this first element. And if it fails, we can figure out why it fails.
Wait, so the top line again, because you showed me this last time I was in your class and I kind of forgot to. It's the top one that printed out was the eigenvalues or eigenvectors.
This?
Yeah, no, I'm saying when you said eigensystem AA and you did the
This?
for a number, yeah, all those values are the eigenvalues themselves, right?
Yeah, well, it's the same as this, right? It's the
Yeah.
eigenvalues. Yeah.
I
And
see.
this eigenvalue corresponds to this eigenvector.
Okay, that's what.
Okay, so we're gonna try it, and we might need to normalize. All right, so we're gonna copy the first entry of each vector into the first row. Okay, and the second row is gonna have the second entry. And then the third row is gonna have the last entry, which are all ones. So, all right, supposedly this this guy is our unitary. But I'm sure it's not quite right. So let's see. I think. Let's see if conjugate transpose does the right thing. We're just kind of, I wanted to show you how you play around with Mathematica a little bit. So let's see if conjugate transpose does the right thing, making sure that this actually does the dagger. And yes, indeed, it does the dagger because you see this gets transposed over here and the imaginary piece picks up a minus sign. So, all right. That indeed takes the dagger. So if I wanted to do BB, if I want to do U dagger U, right? Maybe I'll call this U, right? This should be better. Sometimes you want to, in Mathematica, you want to double up the letter because sometimes it reserves single letters for special commands. So just something to keep in mind. All right. So this is our U. So what if we do conjugate transpose UU into UU? So almost, but not quite what we want, right? It's not the identity because these entries are messed up. And just as someone, was it you, Casey? I forget who mentioned it about the normalization. Maybe it was Peter. Someone said it. I couldn't tell who, but yeah, it doesn't quite work because we haven't normalized the entries. So let's normalize. And what do we have to do to normalize? Well, we have to take each eigenvector, right? And we have to, so this is the eigenvector. Let's see if this, I don't know if this actually works. Okay. I think this should work. Yeah. So if you do v1 dot conjugate v1, right, that should give us the norm squared. So to get the normalized vector, what we have to do is divide all those entries by the square root of this guy. And so then when we do, right, if we take all the entries and divide by square root of this norm here, norm squared, then what should we get when we actually do this? If it's a properly normalized eigenvector, then we should just get 1, right, for this. So let's just check to make sure Mathematica is doing the right thing, right? So it looks like things are fine. So what do we do here? When we're constructing our U, probably should have normalized all the eigenvectors. So we have to divide by this guy. So let's, and what were the entries that we needed? Remember that the first column is the eigen vector that for the first for this first eigenvalue. So we have to take all these first entries in the row and divide them by the normalization. And this guy. All right, so what about the other one? We have V2, right? V2 is the second eigenvector, which is this guy. All right, so we'll do that. This is V2. Again, it's sort of silly, but I guess we can check to make sure everything's kind of working properly. Okay, so if we normalize, okay, we get the right thing, normalize to 1. So we have to take now the second entry in each row and normalize that. Right? And okay, and now we just have to make sure that the last eigenvector is normalized. Oh, we got stuff in chat. Oh, it was Peter. Thanks. Yeah, so we got the third vector and oh, whoops. Yeah, got the third vector here. Let's put it in. Okay. So we got this, and so we have to normalize that. I'm not going to go through this, but check.
Yeah, I thought there was a shortcut, just like Sanka just said, to normalize the vectors without having to do what you're doing manually.
I have no idea, but this is much more educational, right? Because you're sort of seeing how it works. This is very close to what you would do by hand, right? At least I think it's educational. I think it's nice to explore with Mathematica and see what happens. And stuff might go wrong, and that's part of it. But I don't know.
Yeah,
I think it's.
I've never used Mathematica for anything. Is
Yeah.
it useful to learn? Am I going to
Yes.
use it in grad school? I mean,
Yes,
absolutely.
Okay.
absolutely, yes.
okay.
It's very good to learn. Plus, everyone at UT gets a free license, so you can just download it.
I've never needed it for anything. I mean, will we be using it throughout the year?
It'll give you a huge advantage if you do use it, because if I ask you to like diagonalize this or that matrix, sure, I expect you to do it by hand, but you can always go and check in Mathematica.
Okay.
Yeah, I mean, I think it's great. I think it's a great program. I'm a big advocate of it. So
What if we
Yeah.
just use Wolfram Alpha?
yeah, you could use Wolfram Alpha. That's sort of the online version. It's a little bit, it's less nice because you don't get this nice, you don't get the notebook kind of thing, right? But yeah, you could do that.
Plus, Wolfram Alpha is integrated into the full version too, so you can actually add that in this version, and it'll give you a list, just like the online.
Yeah. So all right, we've normalized the eigenvectors and we've put them in the U matrix. And now supposedly if I do this U dagger U operation, it should give me the identity, but I'm worried I did something wrong. So we'll see if it actually works. Did it work? Yes, it worked. So sometimes you get scary stuff like this, right? But if you look at these entries, this is 0. This is 0, right? This is within the sort of numerical precision of Mathematica. So, this is, 10 to the minus 17.0000, So that's 0, this is 0, and this is 1, this is 1, and this is 1. So phew, we did it right? Everything is fine. Okay. That was suspenseful. So, all right, then what about our U dagger AU business? Hopefully that works too. Right, if I do U dagger AU, according to our supposedly solid theorems, this should give us a diagonal matrix, right? So hopefully it does. And yes, it does. Again, it's just hard to see because of the, yeah, I can't actually, I think there's some way to truncate these errors, but let me play around and see if I can get it to truncate. Yeah, maybe not. All right, I can't get it to truncate, but you can parse this, right? We can look at it. Maybe it's easier to see it in matrix form here. So let's look at what this is. This is 0, this is 0, 0, 0, 0, 0. And if you look at the diagonals, you get 3.234. So let's go back and copy our eigenvalues here. Our eigenvalues were 3.323, et cetera, et cetera. Okay, that's right here. negative this guy, that's right here. You know, plus this is just 0. And this guy, which is right there. So lo and behold, everything works. So you can check, you don't have to believe me or these, you know, or when your algebra people when they tell you that it's true, but it's true. It really works. You can really construct a unitary from the eigenvectors normalized, and you get exactly. Oh, is there a question in there? Function in Mathematica to normalize a vector? I don't know. If you find it, Sandcat, you let us know. I don't know. But I like this much better because now you see that how to normalize, right? What do you do to normalize? You take the square root of the vector, you know, dotted into its conjugate, which gives us the sum of the element, magnitude of the elements squared, right? You sum them up. Oh yeah, I can post this Mathematica, sure. Yeah, so I hope it's useful. I just wanted to show you that this stuff actually works, and that's I didn't just make it up. But let's go back to where I'm a little more comfortable, which is just the symbols. All right, so I showed you that you can construct this U from the eigenvectors, and what you get is a matrix that's just filled with the eigenvalues. Ah, okay. So in the chat, there's a command that's called normalize. I haven't heard of this. Let's see what it says. Get the normalized form of a vector V. Well, okay. Yeah, maybe
But
so.
would that work? Like if you're doing the normalization, I mean, you'd have to still, because that's just taking the normal of the vector. I don't think that, could you do like the normalize with that word for the whole matrix?
Well, let's see. I mean, so this is V1. And apparently if you do normalize V1, should give me the normalized version, which supposedly is V1 divided by square root of V2 conjugate V2. What? Oh, sorry, V1. What am I doing? What did I do? All right, here. Okay, yeah, so I guess it just does that. Yeah, all right, you can use normalize, I suppose. Yeah. Thanks. Yeah, that's a good function. I did not know that function. But see, yeah, it does the same thing as taking the vector and just dividing it by its norm, the square root of it, or just, you know, by its norm. All right. Let's do this again. All right. All right, so we've got that going on. And in general, you know, permission is great, but there's a whole set of other kinds of matrices or operators for which we want eigenvalues. So let's make a little table of what happens. This is the kind of matrix you get, and this is the property of the eigenvalues. And as it turns out, all of these kinds of matrices will give you a basis. So all give a basis for your Hilbert space. It gives you an orthogonal set of, you know, whatever the number of dimensions is. It just gives you an orthogonal set of basis vectors. So the one we looked at explicitly here in Mathematica and stuff is this guy, the self-adjoint one, and the eigenvalues here are real. Unitary ones, unitary matrices, they have generally complex eigenvalues, but they all have magnitude 1. Right, it has to be that way because remember, U is norm preserving. So the only way that would work is if the eigenvalues are magnitude 1. And you can prove that to yourself, but what you get is all of the eigenvalues, their magnitude, their complex numbers, they're equal to 1. So one way you can write them is not as these ANs, but you can write them as e to the I theta n, right? So there'll be a bunch of theta n's, however many your dimension of your space. There's also you can put bounds on eigenvalues. If you can show, for instance, that the expectation value, and this is A acting on a vector phi dotted into, phi, you can show that these expectation values are greater than or equal to 0 for all phi, and you can do this, you can prove this sometimes for certain operators. If you can prove that that's true for all vectors in your Hilbert space, then you can show that the magnitudes of your eigenvalues are all greater than or equal to 0. That's kind of not that interesting, I suppose. But an important one.
Wait, what's with the upside down A again?
Oh, right. Good point. So I like to use this math notation. This is in, and this is for all.
Okay.
Okay. And then, and I'll do the third math symbol that's often seen. This means there exists.
Nice.
So, okay, if there exists an operator A inverse such that, and I think there's actually a symbol for such that, but I forget what it is, so I just write such that. There's if there exists an inverse such that A inverse A is equal to the identity. And notice, it's a colon for for such that. Yeah, maybe. Yeah, I think that's right. Colon. Well, we'll do such that. Maybe I'll put a colon. But anyway, if it has a left inverse, and notice it's not the same as unitary. I'm not saying the inverse is like the conjugate transpose or anything. Just if an inverse exists at all, then you know that the eigenvalues are not equal to 0, any of them. Yeah, that's an important one. I think Norman was telling me that. Yeah. Well, yeah, you should have seen something like that in math methods for those of you taking that. The idea is you can only invert a matrix, right, if its determinant is not equal to 0. If its determinant is equal to 0, then you can't invert it. And I talked about that too. Yeah, and exactly. Peter says the product of the eigenvalues is the determinant. So if an inverse exists, then you know right away that the product of the eigenvalues has to be non-zero. And that means that none of the individual eigenvalues can be 0 either, because if one of them is, then the product of all of them is going to be 0. So that's not good. And finally, another very important one is a projection operator. A projection operator always has eigenvalues equal to either 0 or 1. And, the basic idea there is that what are the eigenvectors? The eigenvectors will tell you how your Hilbert space breaks up, right? The eigenvectors associated with eigenvalue 0 are the ones that are orthogonal to the space you're projecting into. And the ones that you actually, the eigenvectors corresponding to eigenvalue 1, those span the space that you're projecting into. And you can see that from the sort of, it's easy to see from the Dirac notation, because if you have like this as a projection operator, right, where X is some normalized basis vector, and this is the only thing. So sort of like having this as your projection operator, zeros everywhere except a single element at like the X position, or, if you're labeling your basis XYZ or something. Then, the eigenvalue 1, that's the thing associated with the vector you're projecting into. But there it might be not just a one-dimensional subspace, it might be two-dimensional. So you might there might be two eigenvectors associated with eigenvalue 1. So, you know, it just depends on what the projector is doing. But all these operators give you a basis. So in that sense, it's, you know, it's Hermitian isn't that special. Basically, any kind of matrix, a unitary or projector, any of the kinds that we're interested in will give you a basis. A set of eigenvectors, basically. All right, any questions about that? Maybe I'll label these. So this is an important one. This is an important one. This one's not so important. This one's kind of interesting because it tells you about inverses, and this is for the projections. The point of this one, I think, is also that so it's not just, so this maybe seems kind of obvious that if this expectation value, let's see, if we have a 4x3 matrix. Do you mean, so the question is, if there's a 4x3 matrix and there are 3 distinct eigenvalues with one dependent, then there's a space.
Yes.
Yeah.
I guess I could have said a 4x4 matrix even, and if we had 3, I guess I should have put eigenvectors, 3 eigenvectors that were linearly independent, but one of them was dependent, then it maps the 4x4 into a 3-dimensional space.
A subspace, yeah. I mean, it still would act on 4-dimensional vectors, whatever it's doing, but if you think about it in terms of a subspace, sure. But you can't really transform dimensions of your space. So, but yeah, I guess so.
Okay, thank you.
I'm not sure. Maybe if, yeah. Linearly. Yeah, I'm not sure actually.
I was gonna say, I don't think that it could go into, you know, when you transform like that, I didn't think that you could go into another space altogether. I thought
No, you
it's
can't.
kind of
So
fine.
I'm actually not sure. I'm not sure the linear. I'm not sure what you mean by, yeah, linearly dependent and dependent. I mean, yeah, I don't know. I'd have to think more about that. I'm not sure. Maybe if you have an example, we could look at it. But yeah.
We could always address it more after class as well if you'd like.
Sure. Yeah, I'm not sure what sort of example that would be. Yeah, I don't really think you can do that actually. All these operators I've listed here, they have orthonormal eigenvectors. Doesn't matter what the degeneracy is or anything. So that's why they're important examples, because they satisfy these conditions, either Hermitian, unitary, they're a projector, or they have a left inverse. Then they have a orthonormal set of eigenvectors. So yeah, I'm not sure you could cook up something that doesn't have that. Yeah, that's right. Okay. So, but sometimes you do get degeneracies, which means you get multiple eigenvectors corresponding to the same eigenvalue. And then those eigenvectors are not unique, because if you have 2 of them, well, you could just add them together in any linear combination, right? And that's still going to be an eigenvector, because if both of these have the same eigenvalue, then A acting on this guy will just give us alpha A psi 1 and then plus beta A psi 2. So this is just A alpha psi 1 plus beta psi 2. So if you have a degeneracy, then any combination of eigenvectors of those degenerate eigenvectors will also be an eigenvector. So it's that entire space. That's why I call it a degenerate subspace, because however many vectors you have, the question is, how do you show that the projector has eigenvalues of 0 and 1? Well, I showed you in class that a projector is Hermitian, so it must have real eigenvalues. And it also satisfies this because that's just the property of a projector. It's Hermitian and it satisfies this, so that means on any eigenvector, it must satisfy, here I'll call it E for the eigenvector. The eigenvalue must, these are all things that must be equal to each other. So the eigenvalue squared must be equal to the eigenvalue itself. There are only two solutions to this equation, and that's 0 or 1. Okay, any more questions? All right, so sometimes you have degeneracies. That means some of your eigenvectors that you find will have the same eigenvalue, and then it's ambiguous which eigenvalues to choose, which eigenvectors to choose, because any linear combination works. So what you typically, and so that's not good. Why is it not good? Because we're gonna need to find a basis for a Hilbert space, a unique basis, where we can actually, uniquely identify it. Like this is basis vector 1, this is basis vector 2, 3, and so on. And we need to do it uniquely without any ambiguities. And so if you have something like if you want to use a Hermitian matrix, say, to get your basis for your Hilbert space, it's not going to be good if there are degeneracies. So if we do have degeneracies, what you often want to do is find another operator called a compatible operator. So if we have our A and it has degeneracies, then we're not happy about that because we can't make a unique basis. So we find another operator, B, such that it commutes with the original operator. And if two operators commute like that, then you can find eigenvectors of both A and B. And the idea is very simple. If you can find eigenvectors for both, it doesn't mean that the eigenvalues are the same. So hopefully B, when you find the mutual set of eigenvectors for both, that B will no longer have that degeneracy that A had. Maybe for those eigenvectors, B has different values. And so it might uniquely identify what happens in that degenerate subspace, right? So if you just use A, you'll get a whole space of degenerate vectors. You can use any linear combination of them to diagonalize, but maybe it's only a particular choice, a particular combination of those vectors that actually diagonalizes B as well. And that's something that happens all the time. And that's those are called compatible operators, ones which commute and for which you can find a set of eigenvectors for both. And it's pretty easy to see that if two things commute, then you can find a set of eigenvectors for both. So if you have some eigenvectors for A and R, this is the labeling the degeneracy, then we know that this is equal to the eigenvalue like this, but we know that these things commute. So this must be also equal to A, B, and comma R. We can commute the A and B. And so so what do I want to say here? So
Well, you might find degeneracies though for in B, so you'd have to go to another one, right? you'd have
yes,
to
so you might
continue
find
all the way down.
that B doesn't break the degeneracy, that it's still degenerate subspace, and then you might have to go find a third operator. And yeah, you find however many you need in order to uniquely identify a set of basis vectors for your space.
So since these commute, we have our A, B, and our degenerate N and our R. And then you would say, would that also go to, what would that be like, A, N? I mean, that was B before, so it'd be A and R, or is this equal to that value right below that, A sub N? I'm writing this down. Because right now you're saying our BA and our ket with their degeneracy and R equals the A and B, and then the ket and R, and then you said, okay, we know that it's commutative, right? The B and A can commute to A and B.
Yes.
And then would that also then equal this AB ket and R equal the A sub N, but this would be instead of B, it would be A there.
No, they're both A. So okay, this is so maybe it's a separate point. The point of this is I'm showing that this object B acting on the eigenvector of n comma R, that vector, whatever it is also an eigenvector of A. So both NR and BNR are eigenvectors. This is just showing how B might break the degeneracy. So if the eigenvalue is non-degenerate, that means there's only a single eigenvector, right? There's only a single eigenvector associated with that eigenvalue. So if AN is non-degenerate, then you know that there's only one vector corresponding to it, and that means that B and R, the only thing it can be equal to is some constant times NR. And maybe I should just call this constant the eigenvalue of B, right? Yeah, this is the point I was trying to make. So if you have a non-degenerate eigenvalue for A, then B acting on the eigenvector also gives you an eigenvector. And moreover, it means it must be proportional to the original eigenvector, because that's the only possible way. The only way, if you have a non-degenerate eigenvalue, means that there's just one eigenvector. And of course, it's, it's only up to normalization. So, any vector proportional to it will also be an eigenvector. But in particular, from the commutativity property, you see that B acting on NR is also an eigenvector, so it must be proportional. And so NR serves as both an eigenvector for A and for B, okay, if it's non-degenerate. If it's degenerate, then it's a little bit more complicated, right? We at least know that B acting on NR will be in that degenerate subspace. So if an is degenerate, then since B and R is still an eigenvector, it must be at least in the degenerate subspace. It must be expressible in terms of a linear combination of the degenerate eigenvectors of that eigenvalue. So if we were, and what does that mean? It means that it might have, in that little subspace, B might have off diagonal elements. So what does this look like in terms of a matrix? This is what it looks like. If you have B, this is the matrix B, in the AN basis. And let me just draw A right in that basis. I just mean the basis for which A is diagonal. So you have A0, A1, maybe this is A1. We'll say it's degenerate, right? A2, A3, and these are all non-degenerate. This is all 0 over here. What would B look like in this basis? Well, it would look like, we argued from point 1 that the eigenvalues which are non-degenerate, like A0, A2, A3 that appear just once, those guys uniquely correspond to, an eigen, those eigenvectors will correspond to eigenvectors of B with their own associated eigenvalues, B0, and the rest is of course 0, 1, 2, 3, 4, 5.
So then it would be like B0, B1, B1, and then there'd be a B2 and a B3. And then we'd associate the B0 and the B2 and the B3 together because those would be our non-degenerative spaces from both, right?
Well, I'm getting there. So these are uniquely identified. So this is
Yep.
what the matrix looks like. This is what it looks like in this space, but we have to be very careful with the degenerate space. So in the degenerate space, you're left with this little 2 by 2. You're left with this little 2 by 2 matrix, submatrix in your B matrix. And we know that we can't really say much. We don't know if B is diagonalized in that degenerate subspace. All we can say is that whatever the eigenvectors of B are for that subspace, we just know that they don't, that they're orthogonal to the spaces of B0, B2, and B3. So in this basis, all we know is that this is just some 2 by 2 matrix. And there's no, these are all zeros. That's what we know. These are all zeros because we know that the space is constrained, because we know that, so property 2, from property 2, we know that this is just a little 2 by 2 matrix, because we know that B and R is in that degenerate subspace, which in this case is a little 2-dimensional subspace, right? Of this 5-dimensional space, and it doesn't mix with any of the other non-degenerate eigenvalues. So but other than that, we don't have any constraints, so we don't even know if it's diagonalized or not. This could be an arbitrary 2 by 2 matrix, so we could put like B10, B12, B13, B14, some kind of entries. But now notice something important, that this guy here, right, the equivalent 2-dimensional subspace of A just looks like the identity matrix times A1, right? In this little subspace, A is just A1 times a little 2 by 2 identity. And again, that's this idea that you can take any linear combination of vectors in that space, and it's still going to be an eigenvector of A. So what does it mean? It means that we are free to diagonalize this matrix. We can use any combination inside that degenerate subspace to diagonalize this little piece. Right? Because in A, nothing changes if we use any linear combination inside that little subspace. We can have any combination we want. We're free. It's an entire two-dimensional Hilbert space we can use for our eigenvectors of A. But B might not be diagonalized there. So what do? We look in that subspace and we see, can we diagonalize that little piece of B? And we know we can do that. We have the freedom to do that because A is just proportional to the identity. And this only works if you have truly degenerate eigenvalues, right? Ones that are exactly equal so that in that little subspace, A is proportional to the identity. And if you do that, if you have that, then you can diagonalize B. And once you do that, then that'll break the degeneracy, right? If you diagonalize this, then we get two eigenvectors in this example, right? In that subspace. And they might be unique. But, you know, it might just so happen that when you diagonalize the little 2x2 guy, maybe you get, again, two degenerate eigenvalues. That could happen. I mean, a very easy example is if this little 2x2 matrix, if it just has 0 here and then, you know, some number B1, B1, right? If it has like exactly the same form as A, well, then you're in trouble because then this is still degenerate, right? We didn't break the degeneracy because this guy is also any eigenvector that's in any vector that's in that 2x2 subspace is going to be an eigenvector of B as well. So you didn't fix anything. But hopefully you see on practical terms how it would work otherwise. It's very important. I think this is probably the best way I've found to explain it. Hopefully it makes sense what happens.
Okay, so this would be actually the steps. So we would have to try to normalize it, and then once we separate our 2x2 in this case, and then we try to diagonalize it, and if we can diagonalize that, we're pretty much finished, right? But if we can't, then we have to go to the next step and try to see.
What would you do? I mean, you would, okay, we did this. Okay, so, okay, what would you do practically? You're given some A.
Yep.
And you find its eigenvalues and eigenvectors. You construct that U matrix, the unitary. You transform the A into this basis where it has all the eigenvalues on the diagonal. And some of the eigenvalues might be degenerate. They might repeat. And that's not good because you then don't know. You can take any linear combination of vectors in that subspace and that will still be an eigenvector. It's not uniquely identified. So then you find some other operator B that commutes with A. And what you do is you write it in the basis of eigenvectors for A. And what will it look like when you do that? Well, for all of the eigenvalues that are non-degenerate, B will have just a diagonal element also because of property 1. Property 2 means that for all of the entries where A has degenerate eigenvalues on the diagonal, there B is not necessarily diagonal. It might have off diagonal elements. And so what we do then is we have to fix that in B and take the right linear combination of eigenvectors of those degenerate eigenvectors to diagonalize B as well. And once you're done with that, you'll have a set of eigenvectors which diagonalize both A and B simultaneously. And that proves this theorem that if you have commuting operators, then you can find eigenvectors of both. So So that's what and this is a procedure for doing it. It's a very practical procedure. You often need to do it when you're trying to construct a unique basis. So that's how it works in practice. All
So
right.
if we need to find a matrix B, is that just kind of a guess and check to see if they commute?
Yeah, good question.
Yeah, usually there's some physical reason
Mhm.
for the choice of B.
Yeah, this is
Usually,
like
okay, so I mean, we'll get to this, I guess, next week, but
Mhm.
operators correspond to measurements. And usually if you have one measurement, then you just specify some other measurement that is like, well, that's compatible with the original measurement, meaning that they don't kind of interfere with each other. You can do the measurements in either order and get the result of the measurements. So it's like taking independent measurements in some sense, but we'll get to it.
okay.
But yeah, there's usually a physical reason why you choose a particular B. And it usually has to do with the kinds of measurements we perform on a system.
So yeah, so going back to what he had said though, because like that's what I was thinking after you explained it, which makes sense. I was like, well, then how would you know what B to pick,
Mhm.
to commute? Because I mean, I was confused there too. So you're just saying it's like two separate measurements. So if I was taking an experiment and I measured it, and then the next day I measured it again, that would be my B, right?
No, it would have to be well, it'd have to be a different kind of measurement. Like,
Okay, so a different total way of measuring whatever I was testing.
just a different property. Like maybe A, you're measuring the spin of something, and then B, you're measuring something else about it, like the mass or something, right?
Okay. Okay.
There's some separate measurement.
So if we're trying to do like a spin squared operator and we get degeneracy, then we can use a spin in the X component or Z component, since we know that those commute.
That's absolutely right. That's the much better example. And we'll
Okay.
yeah, that's right. So if you have a measurement of the total spin somehow, and then you also have a measurement with like a Stern-Gerlach thing or whatever that measures the component of the spin, yes, those would be two compatible measurements corresponding to two different operators. In this case, S squared and SZ. We'll talk about that. And those commute, and yeah, that's exactly right. Yeah. All right. Well, hopefully, yeah, I've been sort of adapting this picture over the years. Hopefully this makes sense with these little degenerate subspaces from a practical point of view. And if you want, I'm not going to do it, but we could, because I don't think I'll be able to make a guess of what, well, I guess I could try, but I just don't think I can make a good guess of what a good B might be. For transform and we don't, and I'd have to cook up some matrix with degenerate eigenvalues. So I'm not gonna, but you can try. You could try using the Mathematica, right, to write down a matrix with some degenerate eigenvalues, and you can try to find a B that commutes with it, right? And so all you have to do is find some B that satisfies that, has this equal to 0, right? When you evaluate AB minus BA. And then what you could try to do is just try applying this conjugate transpose U thing to the B matrix that you find. And I can't quite promise you, but I can pretty much promise you that what you'll find is a matrix of this form. It'll be diagonal in the pieces where A has the non-degenerate eigenvalues, and it'll have some arbitrary little matrix in the places where A is degenerate. Right? And then you could use a combination of those degenerate eigenvectors there to diagonalize B. And then after you've done that procedure, you've now diagonalized both. And what you're left with is a set of eigenvectors for both A and B. And hopefully they're now unique there's one for every single dimension of your Hilbert space, and there's no ambiguity, and you're kind of done. You have a full sort of description of your Hilbert space with unique basis and so on. Okay. And if then that doesn't work, then maybe you have to find a C to help. So, all right. Any more questions? Okay, so the last bit that you actually need for the homework, which sort of, well, and it is just operator valued functions. This might sound fancy, but it's not. It's just the idea that you can take a function of an operator, and that gives you some operator in return. And the only way to define such a thing properly is if you define it as a power series. So any function of an operator is really a power series, some coefficients times a to some power p, where the powers go from 0 to infinity in principle. And why is this useful? Because we know that for diagonalizable matrices, which is all those kinds of matrices I showed you, unitary, invertible, etc. We know that that we can find this D, that's U dagger AU, that's diagonal. But notice we can rewrite this. We can rewrite this as A is equal to U D U dagger. And now I'm assuming that the unitary is both the left and the right inverse, and maybe there's some subtlety in infinite dimensions, but forget about all that for now. I can just take this D, right, and multiply it by U on this side and U dagger on the other side, and that'll cancel these U's, and I get this for A. And now I can use this. This is a very handy thing to use. I can take this and substitute it into here. And now when I do that, right, what do I get? For any one of these terms, I will get U, D, U dagger, then U, D, U dagger, however many times, P times, right? That's what A to the P is. A to the P power. Okay, but all of these are just the identity. So I can get rid of all those. And what I'm left with is the coefficients. Then we're left with a U. Then D, the diagonal matrix, appears P times, right? And then you've got the leftover U dagger in the end from the last A. So what is this? This is just the function of the diagonal matrix, right? Transformed by U and U dagger. And we know how to do functions of a diagonal matrix, because if you have a diagonal matrix, you take the function of it, whatever it is, like sine or cosine or exponential, whatever it is, if it just has diagonal elements like that, then I can just take the function of the individual elements. You still get out a diagonal matrix. So whatever the function is, maybe it's squared, or I don't, whatever you're looking at. Maybe it's the log. Then we know how to take the function of a diagonal matrix as just a function of the individual elements. There's no funny business with the matrix aspect of it, because there's no off diagonal pieces. And that's really how you define a function of an operator. You think about it in terms of its power series. What else? So I talk about different types of functions in the notes, and I don't know. Well, I don't know what to say about it. We won't So an interesting function of an operator is something called the resolvent. And notice that you can do things like, so for the homework might be relevant, you can take a function, right, and multiply it by a constant times a matrix. And now you can do things like Taylor series in lambda if you wanted. You can do things like that. And as long as you just think about things in terms of the function power series, you can work with objects like this. So you'll practice that on the homework and hopefully it's not too bad. But ask me questions if you're stuck on that particular.
So in that case, since you just showed us what you had above there, if we're just taking that function of that matrix, that matrix is just the diagonals, right? With a constant that we can multiply by. So it'd be that f lambda 1, f lambda 2, but multiplied by constant a, right?
Yeah, but you can now do things like differentiate with respect to that constant. You can do things like this. And that's sometimes useful because sometimes you get a relationship. You get like a differential equation for f, which you can solve. So you'll practice doing something like that on the homework. I don't know what else to say about it other than like going through the homework, but maybe we'll do it for recitation. But yeah, you should be able to look at it. I mean, I know the homework's due next week.
Wednesday.
In exactly a week, Thursday, right?
Oh, it's Thursday. Oh, yeah, it's the 9th, so that is Thursday.
Yeah, so it's due in exactly a week. So just try this problem. I think that's the most sort of advanced problem on the homework in the sense that,
So what would we take a differential, like let's say our value of that function. I mean, since we can do that, what is that really like besides like, I know if you take a derivative of, velocity, acceleration, but what would that give us? Why would we want to do the derivative though for that particular value of that function? What extra does that give us though? I mean, you say that, could you just, I know it sounds like something I should know, but I just wanted you to reiterate it.
You might want to do it to prove something like that you might be able to show that derivative of this is equal to the function itself. And then that's a differential equation for f, which you can solve. The solution to this is just that f has to be an exponential function. So you can use it to prove then that, f lambda a is equal to some constant e to the lambda a, for instance. So you can use it to actually solve for f, which is the kind of thing you do on the homework. But there's lots of ways to do it for the homework problem. You can also use this as a Taylor series, and you can like prove that the function is equal to another function that like an exponential by just comparing the Taylor series. Like that the Taylor series for an exponential is, right, sum over n, 1 over n factorial, right, x to the n. So if you can prove that your function, that these are your coefficients, then you know that your function has an exponential form, right? So it's, basically because of this property that the operator can be diagonalized, and you can write it in terms of just the function of the diagonal elements of the eigenvalues, then in a lot of senses you can just treat a function of an operator as you would any function. And you're but it's it's a little bit subtle because you do have to think about it as a power series, and so it means if you do something like this function of a product of two things, you have to be very careful that the a and b stay in the right order and so on. So you have to be a little bit careful, but for the homework, you're just trying to see how functions of an operator behave like regular functions. in a sense. Okay, so the resolvent is an interesting function. I'll just mention this. It's defined as 1 over z, which is some complex number identity, minus a. And this is a function, it's called the resolvent. It's a function of both z, the number, and a, the operator. And what happens is that this thing, when z is a eigenvalue of a, then this thing blows up, right? Because, well, because if you imagine this object acting on an eigenvector or something like that, then you'll get that you get an eigenvalue minus the eigenvalue, right? And that gives us 1 over 0. So it blows up. So this has poles, singularities, whenever z hits an eigenvalue of a. So it's an interesting object. And then for infinite dimensions, it'll be a way of thinking about the eigenvalue equation for an infinite dimensional Hilbert space in terms of the resolvent. So we'll go back to this later. Okay, and so that's just an example of one of these functions that's used. We'll go back to this later. It'll be important for infinite dimensional Hilbert spaces. And the last thing in the last 2 minutes here, I just wanted to mention that we'll also be dealing a lot with probability. That's the other piece of mathematics that is important for quantum mechanics. Quantum mechanics is just really linear algebra plus complex numbers and probability. So that's the mathematics of quantum mechanics. So you kind of have to know all of them, all those pieces, but a lot of times probability is sort of swept under the rug a little bit because well, we just calculate the probability and we don't really think about what probability means and so on. But it's worth thinking about, and I put a little bit in the notes about like the mathematical axioms of probability. Maybe I'll mention it at the beginning of class next time a little bit, but just some basic things is that probabilities are always positive, and to define a probability, you need 3 kinds of things. You need an event space. Then you need a sample space. And you need the actual distribution or the measure, the thing that actually measures the probability, which is P. And what you do, and then there's a set of axioms written down by Kolmogorov, and it says that the probability of any event is greater than or equal to 0. And events live in our event space. And the sample space is, it's the set of all possible outcomes. So like, for instance, if you have a coin flip, the sample space would be heads or tails, right? That's, and the event space would be all the different things that could occur in our coin flipping, endeavor. So what could occur? Well, first of all, maybe nothing happens. And the probability that, so this is called the empty set. So this is nothing. So the probability that nothing happens is 0. Something will happen. Then you can have maybe heads. So all these things are subsets of, they're basically sets of pieces of the sample space, right? So you can have your event space could be nothing happens, it could be heads, or it could be tails for a coin flip, or it could be either heads or tails. So it's the set of heads and tails as the 2 different possibilities. And so then the probability of any one of these events is going to be always greater than or equal to 0. And then there's also like some special cases, the probability that something happens, anything in that sample space, the list of possibilities for the thing, that's always greater, that's always equal to 0. And that's the normalization of probability. And that's why we have to normalize all our vectors to 1, essentially. And we'll talk a little bit more about probability next time, but it's worth thinking about the kind of axiomatic approach to probabilities, because it actually is ingrained into quantum mechanics in a kind of fundamental way. Well, yeah, I guess we'll talk about that next time. Any? Oh, is the
James had a
event space the
question.
power set of the sample space? Yeah. Yeah, it's the set of all subsets of the sample space. All right, well, thanks everyone. I'm around today for questions.
When are we going to have your recitation? Is on Monday again, or is it going to be on Wednesday?
I think since we're doing alternating weeks, the next one's on Wednesday. So I guess right before the homework's due. So if you do have questions about homework, you can ask me before then. Wednesday will be sort of last chance, you know, these people.
Let's do a law tech.
Yeah.
I'm not going to turn it right now. All right. Thanks a lot for this